Hello mathematicians, we're going to take a look now at second and higher order derivatives. So the second derivative, which is denoted f double dashed of x, is the rate of change of f dashed of x. So it's the rate at which the gradient changes. So if you like, it's the rate of change of a rate of change in a way. Now if we realize that we can also write it as y double dashed or d2y dx squared, and these are all the same sorts of things, then as far as determining higher derivatives goes, we don't need any new theory because we follow exactly the same procedures as if we were finding the first derivative. So we have our product rule, we have our function of a function rule or chain rule, we have our quotient rule, and we have to be careful in all the same ways that we were careful with finding the first derivative. However, the second derivative has some significance which makes it worth finding. But before that, if we just practice a little bit finding the second and higher derivatives, there's no reason why we should stop at the second derivative, but in this course essentially we do. But you could go on to a third, fourth, fifth. They become a little bit meaningless after a while. So in 10D, there are these questions to have a go at. And we're going to have a look now at how concavity and points of inflection can be investigated with the second derivative. So if the second derivative at a point A is negative, what that tells us is that the curve is concave down. And we'll see why that's the case in a moment. If the f double dashed of A is positive, the curve is concave up at x equals A. So if we think about this curve just here, so this would be a case where we've investigated the curve, we've found that there's a spot where f dashed, at x equals A, where f dashed of A is equal to 0. So that's a stationary point. And to investigate the nature of that stationary point, we would have investigated the first differential either side of that point with a little table. Now if we take the second differential and it's less than 0, what that second differential says, if it's less than 0, is that the rate of change of the gradient is always negative. So if we think about what the gradient would look like here, we can see that it would be a large positive value, and it's becoming a smaller and smaller and smaller positive value until it's 0 just here. And now it's a negative value and it's becoming a bigger and bigger and bigger negative value. So our gradient itself is always decreasing. So we've come across the concept of a curve that's decreasing when the gradient was always negative. Now we're looking at the fact that when in a sense, the gradient of the gradient, the rate of change of the gradient, when it's negative, it means that the gradient is always decreasing. And as we read left to right in our numbers, we can see that that's the case. We've gone from a positive down to 0, down to a negative, and an even bigger magnitude negative. So that's a constant decrease. And we can see that this curve is concave down. And similarly, we could go through the logic of a curve which was concave up, and we could say that initially we had a large negative gradient, and the magnitude of that negative gradient was getting less and less and less till it got to 0. Then it was positive, and it was getting to be a more and more positive number. So that all the way across from left to right, as we've been observing the gradient, we've seen that the gradient has been increasing. So if we have this constant increase in the gradient, then what we have is the condition for a concave up curve, which is where we have a minimum turning point. So in your head, you're going to really need to clarify those connections. So just once more, if we have a stationary point, that occurs when the first differential is 0. If we have at that stationary point the second derivative being less than 0, then we've got a maximum and the curve is concave down. If the second derivative at that point is positive, then we've got a minimum and the curve is concave up. So that really has to be hammered home and sort of at your mental fingertips in a sense all the time. Now the second derivative, well, we've already covered this, can really be used to test the nature of a stationary point. So we've talked about this already. So maximum turning point where second differential is negative, minimum turning point where the second differential is positive. So we now, as always, have things that we have to be careful of. And one of these is where both the first differential is 0, which indicates a stationary point, and where the second differential is 0, we need to actually do more work, because it's possible that this could be a horizontal point of inflection. But for us to know for sure that that's the case, we need to check the concavity either side. So if the concavity either side of this point is unchanged, which is not the case here, then we need to be careful. So we've got that the slope is positive here and the slope is positive here. So there's no change in the slope, but the curve was concave down there and is concave up just there. So we've now got an expanded definition for a horizontal point of inflection. We've got it being a point where concavity changes, but slope doesn't change, and where the tangent crosses the curve. And likewise for this one. It's concave down, concave up, but negative slope, and it's supposed to be horizontal, 0 slope in between. So we really need to be careful about making sure that we've satisfied the conditions for a point of inflection. Because it is possible that we could get the first differential being 0 and the second differential being 0 and find that we did actually have a minimum or a maximum. Now that happens with higher powers. So things like y equals x to the fourth, for example, which ends up, if we graphed it, showing that we've got something like a squared off minimum that has the first differential and the second differential at that point equal to 0. But it's clearly not a horizontal point of inflection because concavity doesn't change and slope of the function does change. So we need to be clear about what constitutes a point of inflection. So here's a table, just again reinforcing those things that we've spoken about just here. So this is the key. An inflection point is a point where concavity changes. Now it's possible to get an inflection point where it's not a stationary point, and that occurs when we have something like this. So on this curve here, what we can see is that we can have at some stage the curve switching from being concave down to concave up and back to concave down, and that point is somewhere in here, which is definitely not a stationary point, but it is a point of concavity changing. So it's an inflection point, but it's not a stationary inflection point. So at these points here, we have that the first differential is not equal to 0, but the second differential is. So we're having a change in concavity. It's also worth noting that the inflectional tangent, so the tangent at the point of inflection, has its greatest magnitude at the inflection point. So for this example here, we want to determine the nature of the stationary points for this graph and sketch the curve. So we need to take the first differential, find where it's 0 to get the stationary points, and then find the second differential at those points. Now, so you don't have to watch me write, I'll put that down now. So you can see our first differential, when we factorise it, is going to give us values of 0 and 3 to make the first differential 0, in other words, to give us a stationary point. And so the points themselves, when we put these x values back into the original function, will be 0, 0, and 3 minus 27. Now, to get the nature of those stationary points, we would have in the past drawn up the little table But now we're just going to take the second differential. So the second differential is just differentiating this one again. So that will be 12x squared minus 24x. Or again, I'll just take out a common factor, 12x outside of x minus 2. So what we need to do is to use this to get the nature of these stationary points. So at x equals 0, we have that the second differential at 0 is actually going to be 0. So this is a possible point of inflection. We will have to investigate this with the table. But at x equals 3, f double dashed of 3 is going to give us 36 times 1. So the main thing is that it's a positive, therefore it's a minimum turning point. So now we have to investigate this one a little bit further. So we need to draw up our table. So for our values of x, we're going to look at minus 1, 0 and 1, and we'll investigate the second differential, and we might as well investigate the first differential as well. So when x equals 0, we know that our second differential is 0 and our first differential is 0. When we put minus 1 into our second differential, this term will be negative, so negative 12x. This one will be negative as well, so altogether that's a positive. And if we have a positive value for f double dash, that means it's concave up. When we get to plus 1, this will be 12x will be positive, this term in brackets will be negative, so we get negative altogether. So negative f double dash means concave down. And if we think about the slope as well, then when we've got minus 1, if we look back up at our slope equation up here, then this first term will be positive because it's squared and it's times a negative. So we've got a negative slope there, which will look like this. And when we put x equals plus 1 in there, first term again is positive, second term is still negative, so we've got a negative slope. So what this table tells us is that we have a change in concavity from concave up to concave down, and that the slope doesn't change either side, so this is indeed a horizontal point of inflection. So now we put those clues together and try and sketch it. So if we look at this sketch here, here's our minimum turning point at 3 minus 27. Our point of inflection, horizontal point of inflection going through the origin. Now normally it's not easy to find where we cut the x-axis for these higher powers, but if we look back up at this original function, I could take x cubed out of x side x minus 4, so I can see it will cut at x equals 0 and at x equals plus 4. First part of our next example says show that if y is this, then y double dashed is that, so I'll just do that. We can see as we run through this with the quotient rule, this is our first differential here, and then we apply our quotient rule and get our second differential. We notice that we've got plus 10 times x minus 3 over x minus 3 to the fourth, so one of the x minus 3's cancel, and then we've got this set up here. Now it then says by examining the sign of x minus 3 cubed, because that's the only part that can change, determine when the curve is concave up and when it's concave down, and sketch the curve. And of course we can't have a point where we've got y double dashed equal to 0 because the top is 10. So no potential horizontal point of inflection there, and in fact there's no stationary point because there's no possible value of x which will make the top line of y dashed equal to 0. What we do notice is that we're never allowed to have x equal to 3. So there's going to be a vertical asymptote at x equals 3. So the curve doesn't exist. the first differential doesn't exist, and so it's sort of meaningless talking about concavity there. So if we look at our second differential and notice what happens with the bottom. So we know that if that number on the bottom, x minus 3, is a negative, when you cube a negative, you'll still have a negative. So that means that if x minus 3 is less than 0, therefore that means that if x is less than 3. So to the left of our discontinuity here, we're going to have the second differential being negative, which means that we're talking about concave down. And to the right of our asymptote, that's when we will have the second differential being positive, meaning concave up. So we've got concave down to the left, concave, did I say that right? Concave down to the left and concave up to the right. We have no turning points, but if we have a look back at our original function, get my pen to work, then we can see that we cut the axis, cut the x-axis when y equals 0, which will happen when x equals minus 2. So that's here. We are not going to cut the y-axis when x is 0, which will be negative 2/3. So given that our curve is always going to be concave up, it's going to go something like this. Sorry, always concave down, it's going to go something like this. Now, our curve where it's concave up, and given that it doesn't cut through this axis anywhere else, it can't be like this shape. It's got to be trapped up in here. Now for our last question, we want the equation of the tangent at the point of inflection. So the point of inflection is where the second differential equals 0. So let's put that down. So we've got our first differential, which is the slope, second differential, which is 6x plus 6. That has to equal 0 for a point of inflection. So that will occur when x equals minus 1. And if we put minus 1 back up into our original equation, I think that gives us 88. So we've got the point of inflection. Now, if we're going to get the equation of the tangent at the point of inflection, we need the slope of the tangent at the point of inflection. And the slope of the tangent at the point of inflection is the slope of the curve at x equals minus 1. Which means we need to look at our first differential and put minus 1 into that, which will give us 3 minus 6, which is minus 3, minus 72, so that's minus 75, very steep, but we know that they're steepest at the point of inflection. So then we come to our gradient intercept, our gradient point formula. So y minus y1 equals m outside of x minus x1. So that will be that. So we get 75x plus y. That will be minus 75, and we bring that across. So that'll be minus 13, I think. So that's our equation for the tangent at the point of inflection. And have a go at these.